This is the first lesson of Unit 8, Algebraic Vectors. We can use a Cartesian coordinate system to work with vectors in either 2D, r squared, or 3D, r cubed space. We call these algebraic vectors. We'll start with doing algebraic vectors in 2 space. We can represent a vector on a Cartesian grid by placing its tail at the origin. Then the tip of the vector will be at some point AB. So we've got the tail at the origin, and then P is the point AB, and so the vector is given as A, B, because it goes from the origin to that point. So this is a specific type of vector. It's called a position vector of a point AB, of a point P is the vector OP from the origin to the point. While a geometric vector can exist anywhere in space, algebraic vectors typically have their tails on the origin right here. Okay. Any vector u can be written algebraically as an ordered pair. U, OP is equal to AB. Here we can see that O represents the origin and P represents the point AB. The magnitude is given by the absolute value of u is equal to the square root of a squared plus b squared. The direction is given by theta equal to tan inverse b over a, where theta is measured counterclockwise from the positive x-axis to the line of the vector. And so if we're measuring theta counterclockwise from the positive x-axis, that means that theta is in standard position. Let's keep going with unit vector notation. Another common notation for algebraic vectors uses unit vectors. We define I cap or I hat equal to 1, 0 and j cap being 0, 1. So I cap 1, 0 is the unit vector along the x-axis, and it's a unit vector because it has a magnitude of 1. And it's going from the origin to the point 1, 0, so we can see it's right along the x-axis. J cap is essentially the exact same thing. It's got a magnitude of 1, and it's along the y-axis. The ordered pair and unit vector notations are equivalent. So ordered pair notation is what we just saw. Remember, the vector goes from the origin to some point P, and so we give the ordered pair being the point where the vector stops. You can see right where my cursor is right here, right? So that's the point where the vector stops because we know that it's starting at the origin. Okay, and A and B are components of the vector u. So like it's going all the way to this x value A, and it's going as high as the y value B. So we can use unit vector notation by saying, okay, u is just basically some A value multiplied by the unit vector in the x direction, and then some B value multiplied by the unit vector on the y direction. So if we took this right here, essentially what we are saying here is we are saying we're going to go and we're going to do 18 times the unit vector along the x-axis, then 13 times the unit vector along the y-axis. So if we think about that, 18 times the unit vector along the x, 13 times the unit vector along the y, how would we represent that using unit vector notation? See if you can pause the video and figure it out for yourself. Okay, and so here we have it. OP, going from the origin to the point P, is going to be 18 times I cap plus 13 times j cap. Okay, and you can think of OP as the resultant of adding 18 I cap plus 13 j cap. OP is the resultant of that vector addition. Okay, let's keep going here. Express the position vector of each point as an ordered pair and in unit vector notation. So here we go. I've got my vectors right here. like OP is going from O to P right here. So ordered pair notation, well, that would just be 6 comma negative 2. But let's think about that in terms of unit vector notation. Well, it's got to go 6 units along the x-axis and then negative 2 units down in the direction of the y-axis. Okay, so let's think about using unit vectors here and see if you can figure this one out. 6i cap minus 2j cap. Okay, let's do OQ, and I'm just going to change the color of this arrow so that we can distinguish it from the other ones. OQ goes from the origin to point Q, negative 3, 3. So try doing the ordered pair and the unit vector notation and see if you can get it yourself. Just hit pause and see if you can figure it out, and then the answer will show up. Okay, and there it is, negative 3, 3, negative 3i cap plus 3j cap. All right, and the final vector. And there's the answer for vector OR. Okay, moving right along. Okay, draw the position vector for the point negative 5, negative 7 and determine its magnitude and direction. Well, we can see right here, this is like roughly negative 5, negative 7, right? So what I'll do is I'll put my position vector right there. Or my, sorry, that is my position vector, but I'll put point negative 5, negative 7. Okay, there we go. And all right, so let's determine its magnitude. So if I want to find the magnitude of this position vector, we previously saw the equation of that is the square root of a squared plus b squared. We know that that just means that we're using Pythagorean theorem there. So see if you can then figure out the magnitude of OP. Okay, well, the magnitude of OP is the square root of negative 5 squared plus negative 7 squared, which turns out to be the square root of 74. Okay, so I've got its magnitude, and the question is now asking me also for its direction. So recall that direction, we're going to give direction as theta measured counterclockwise from the positive x-axis to the line of the vector. So let's go back over here and let's do my tan inverse of a negative 7 over negative 5, which is b over a, right? Again, we're using this formula right here, the tan inverse of b over a, and in this case, my b is negative 7 and my a is negative 5. Okay. The only issue is when you go ahead and you do this, you will find that you are going to get theta, or at least your calculator is going to give you theta is equal to 54 degrees. The issue with this is that we can see that this angle is not 54 degrees because this angle would put us into the third quadrant. So 54 degrees would have us in the first quadrant. That's not possible. So I'm going to put an X beside that and identify that that is in quad 1. So what I need to do is I need to find what is this angle from the positive x-axis all the way to this position vector right here. Well, in order to do that, I need to go 180 degrees and then I need to add that angle of 54 degrees. So here it is, I'll show you right here. It's 180 degrees plus 54, that would put me into quad 3, and so the angle is 234 degrees. Okay, let's look at this one right here. Express u as an algebraic vector if its magnitude is 10 and its direction is 60 degrees west of north. So what I'm going to do here, I've got the vector right here, 60 degrees west of north. So that's 60 degrees, making that 30 degrees. Well, if this is 30 degrees, you can see that this is going to produce a special triangle here. Okay, so I'm going to put my magnitude along that right there, and my magnitude is 10. And I'm going to construct a right angle triangle so you can see that this is in fact a special triangle. Okay, there we have it. Now, the special triangle that I have, if the angle right here is 30 degrees, well, that means that this side right here is similar to negative 3. Sorry, not negative 3, negative root 3. The y value, or the height, is 1, and the hypotenuse is 2. So that's my 60, 30, 90 special triangle. Okay, So what I'm going to do is I'm going to put up some formulas here because I need to find A and I need to find B. A being the scalar, you can see right here, A being the scalar of the I cap vector, and B being the scalar of the j cap vector, right? So A is the x component and B is the y component of this vector right here. And so I need to express it as an algebraic vector. So I need components A and B. I'll go ahead and I'll put up some formulas. Okay, so the first equation that we're looking at is cos theta is equal to x over r. And we know that as the definition of cosine when we're doing rotational trigonometry. I'm going to put in some values here. So we know that theta would be 150 degrees. And that's because we define theta as being the angle from the positive x-axis all the way to the terminal arm. So I'll just move that over a little bit. Okay, so that's 150 degrees. So cos 150 degrees is x over r, so negative root 3 over 2. But in this vector, I don't have negative root 3, I have a, and my r value isn't 2, it's 10. So I can redefine this right here as being cos 150 is equal to a over 10. Well, if cos 150 is equal to a over 10, and cos 150 is also equal to negative root 3 over 2, then I can equate these two values. So negative root 3 over 2 is equal to a over 10. Okay, and so I'm going to rearrange and simplify now and solve for a. First, I multiply both sides by 10, so I'm going to have now negative 10 root 3 over 2 is equal to a. And then negative 5 root 3 is equal to a by simplifying the negative 10 over 2 to just negative 5. Okay, so I have my a component. Now I need to find my b component. And so to find my b component, I'm going to take advantage of the sine trigonometric ratio. Sine theta is defined as y over r. So similarly, in this case, my theta is 150 degrees. So I'm going to write sine 150 degrees is equal to, so 150 degrees is equal to y over r, so 1 over 2. Again, though, 1 over 2 are not the values that I have in this vector. My y value here is b, and my r value here is 10. So I'm going to write sine 150 is equal to b over 10. Okay, so since both of these things equal to sine 150, just like I did in the last question, I'm going to equate 1 over 2 to b over 10, and then solve for b. Okay, so 10 is times 1 over 2 is equal to b. If you're wondering how I got that, okay, so basically this 10 right here, I'll just select this 10 so you can see it. This 10 right here was, as we saw, underneath the b, and I multiplied both sides by 10, which is why the 10 is now on this side over here. 10 times 1 over 2 is equal to 5, so 5 is equal to b. So I have my a component, that's negative 5 root 3, and my b component is just 5. So I can write this vector now as an ordered pair. So therefore u is equal to negative 5 root 3, that's my a component, and then 5 is my b component. I can also use unit vector notation. So that's my scalar times the unit vector in the x direction, and this is my scalar times the unit vector in the y direction. So u is equal to negative 5 root 3 I cap plus 5j cap. Okay, so that is all algebraic vectors in 2 space. But now we're going to look at algebraic vectors in 3 space. So we've got the x-axis, the y-axis, and the z-axis as well. And we have ordered triples, x, y, and z. We have 3 planes. We've got the xy plane, which is sitting, on the floor here, so to speak. And then the 2 walls are xz plane and yz plane. Okay, and we still have unit vectors along the x direction. along the y direction, but also along the k direction, which is along the z-axis as well. So for a vector u in 3 space, we can write it just like we did in 2 space as an ordered pair, but in this case it's going to be an ordered triple, a, b, c. We can use it in terms of unit vectors, so this is similar to what we did in 2 space, but now we're doing it in 3 space. Magnitude is also takes advantage of Pythagorean theorem. Okay, so the magnitude of u is equal to the square root of a squared plus b squared plus c squared. And given the 3 different angles, alpha, beta, and gamma, called direction angles, these are the angles that the vector makes with the positive x, y, and z axes respectively, where each angle can only be between 0 and 180 degrees. Okay, so these are the angles that they make with the respective x, y, and z axis. You can see a diagram right here. The direction angles are also given by the formulas. Cos alpha is equal to a over the magnitude of u. Cos beta is equal to b over the magnitude of u. And cos gamma is equal to c over the magnitude of u. Cos squared alpha plus cos squared beta plus cos squared gamma is equal to 1. This means that if you know 2 of the direction angles, we can find the third. In 2 space, a point can be on the x-axis, the y-axis, or any one of the 4 quadrants. In 3 space, a point can be on the x-axis, the y-axis, the z-axis, and also on a plane, the xy plane, the xz plane, the yz plane, or in xyz space. So obviously many more places a point can be in 3 space. Okay, so I think the answer is kind of given there, so I'm going to pause for a second and get rid of that. Actually, never mind. Let's just take a look at this. Locate the point P, sketch the position vector OP in 3 dimensions, and calculate its magnitude. Draw the x-axis, the y-axis, and the z-axis in the first example. So we're drawing the x, y, z-axis. I just copied and pasted it from the other question. So there's my x-axis, there's my y-axis, and there's my z-axis. So where's this box coming from, this 3-dimensional box? Okay, well, let's look at it. -5 is the x component. So I'm going to go -5 back along the x-axis. So I'm going in that direction right there. Okay. Now, I also have to go -7 along the y-axis. So I go -7 along the y-axis, which means then I still have to go -5 along the x-axis. So I go -5 along the x right here, and then -7 along the y right there. The last component is my z component, which means I've got to go up 2 units. So I go up 2 units, up 2 units, up 2 units, up 2 units, and then I make this prism, and this vector right here goes from the origin to this top corner right here. That is P, -5, -7, 2. Okay, so that's that point right there. We can see it's -5 units back along the x-axis. It is -7 units along the y-axis, but then it's 2 units up along the z-axis. Okay, now we have to find its magnitude, and we saw that the magnitude of a vector in 3 space is just given by the square root of a squared plus b squared plus c squared. So I'm just going to take that formula and I'm going to use it and evaluate the magnitude of this vector OP. Okay, and there we have it. The magnitude of OP is equal to the square root of -5 squared, that's my A, -7 squared, that's my B, and 2 squared, that's my C, and I get the square root of 78. Okay, for OP over here, again, we're going to go take a look at how this is formed. This is my x component, this is my y component, and this is my z component right here, -4. So I need to go 3 units along the x, then 5 units along y, and then down 4 units along z. And so I create this 3-dimensional prism here, knowing that it's going to go from the origin to this point right here on the prism, which is, again, 5 units along your x, 5 units along your y. It is 3 units along the x, and it's -4 units down along the z. And so that's my point 3, 5, -4. To evaluate its magnitude, again, I'm just going to use this formula right here, which is, again, like I said, it takes advantage of the Pythagorean theorem. So the magnitude of OP is equal to the square root of 3 squared plus 5 squared plus -4 squared. And then that's equal to the square root of 50, but the square root of 50 can be simplified. So the square root of 50 can be thought as 2 times 25, 25 being a perfect square. So that's going to simplify to 5 root 2. And there we have a simplified magnitude of vector OP. Okay, in these questions right here, it says describe where the set of points is located. So 0, 1, 2, 0, 5, -1, and 0, -3, -2. Well, perhaps you saw right here, and I'll highlight it for you, that the x component in each of these is 0. So if the x component in each of these points is 0, that means that it has to be located on the YZ plane because it doesn't have an x component. It only has a y component and a z component, so it's going to be on the the YZ plane. Yeah, the x component is 0, so only y's and z, so YZ plane. Okay, looking at the next one, we have 7, 0, 0, -3, 0, 0, and 2, 0, 0. And so for those ones right there, you see that there is absolutely no y and z component, and their only value is the 7, the -3, and the 2. So there's only a point on, these are only points along the x-axis. The y and z coordinates are all 0, so this one is just on the x-axis. These sets of points are only on the x-axis. Okay, it says find the direction angles of vector u, 0, 5, -3. Okay, so 0, 5, -3, so there's my A, there is my B, and there is my C. So I'm going to go ahead and I'm going to give all the different formulas that we use to find the direction angles. So I'll write those out. And then you can see that in each of these formulas, I need the magnitude of the vector for the denominator. So let me write out the formulas. Okay, so here are my 3 formulas. Now, like I said, I need the magnitude of vector u. So I'm going to go ahead and calculate the magnitude of vector u using the formula and A, B, and C. Okay, so there it is. 0 squared plus 5 squared plus -3 squared. Well, that's going to be 25 plus 9, which then just equals to the square root of 34. Okay, so now that I have the magnitude of vector u, and I have A, B, and C, I can use these formulas right here to find all my various angles. So let's just start with the cosine of alpha. So the cosine of alpha is equal to inverse cosine 0 over 34, or rather alpha is equal to the cosine inverse of 0 over root 34. Right, as you can see here, I'm trying to isolate alpha, so I just take the inverse cosine of both sides. That eliminates my cosine there, and I have this right here. So alpha is 90 degrees. And this makes sense because the vector is on the YZ plane, and if the vector is on the YZ plane, well, that means that it's going to be 90 degrees from the x-axis. Moving on to beta. So I'm going to do the same thing here. I'm going to isolate beta and take the inverse cosine of both sides and sub in my b value of 5 and my magnitude of u as root 34. Okay, so there we have it. And now evaluating that, I should get beta is equal to 31 degrees. There we go. Okay. Finally, cosine gamma is equal to c over magnitude of u. So I'm just going to go ahead and I'm just going to put that in and solve for it. And there we have it. So my alpha is 90 degrees, my beta is 31 degrees, and my gamma is 121 degrees. Okay, and those are my direction angles for that vector. Okay, in this example here, a vector u makes an angle of 55 degrees with the x-axis and an angle of 110 degrees with the y-axis. What angle does u make with the z-axis? Okay, so you can see that I'm given some position or some direction angles for vector u. So recall that I have this formula that I can use. Cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. And alpha is already given to me in the question. It's 55 degrees because that's with the x-axis. And beta is given to me as well. That's 110 degrees because that's with the y-axis. So I need to find the angle gamma that it makes with the z-axis. So let's go ahead and sub some values in. Okay, so there we go. Cosine squared 55 degrees plus cosine squared 110 degrees plus cosine squared gamma is equal to 1. So let's isolate cosine squared gamma. So cosine squared gamma is equal to 1 minus cosine squared 55 minus cosine squared 110 degrees. I need to evaluate that and then take the square root of both sides. Okay, and notice that I'm going to use an approximate symbol here because we're only going to 3 decimal places for this side of the equation. Okay, so recall if I have a square root and the index, because it's square root, the index is even, then I need to be thinking about taking the plus or minus of my resulting value. Okay, so cosine gamma is equal to plus or minus 0.744. So then I need to evaluate both the positive and the negative cases. And so I'll do those simultaneously. Okay, so you can see here I've got the positive one, 0.744, and over here I've got the negative 0.744. Okay, so evaluating the positive one, I'm going to inverse cosine both sides and then evaluate that answer, and I should get 42 degrees for gamma. For the negative, I can take the exact same process, and if I find this right here, my gamma should be 138 degrees. Okay, and there we have it. So there's 2 possible answers here, 42 degrees for gamma or 138 degrees for gamma. Okay, so those are the 2 possible angles it makes with the z-axis. Okay, last example. Write a unit vector that is collinear with d, d being defined as 3, -2, and 4. So vector d is 3, -2, and 4. Then prove that it is a unit vector by determining its magnitude. Okay, so what I'm going to do right here is I'm just actually going to find the unit vector d. And I can do that by taking vector d and multiplying it by a scalar 1 over its magnitude. So that means I need to find the magnitude of vector d. And this is something that you've seen, like this formula right here, we saw in the previous unit. Okay, so there's my formula for the magnitude of vector d. 3 squared is equal to 9. -2 squared is equal to 4, and 4 squared is equal to 16. So I've got 9 plus 4 plus 16 all square rooted. And that should give me the magnitude of d is equal to square root of 29. Okay, so now that I have the magnitude of d, I can just write that d cap is equal to 1 over the square root of 29. And then times vector d, which is just 3, -2, and 4. Okay, and there we have it, which abides by this formula right here. Okay, so this is a scalar, which means it's going to distribute to all the different components. So this should be 3 over square root 29, -2 over square root 29, and 4 over square root 29. And there we have our unit vector that is collinear with d. And we have to verify that it is in fact a unit vector. So we're going to check its magnitude. It says determine its magnitude right there. Okay, so if we want to find the magnitude of this vector, we're just going to use the formula that we use to find the magnitude of the other vector. Okay, so there it is, the square root of 3 over 29 root 29 squared plus negative 2 over root 29 squared plus 4 over root 29 squared. Applying all the squares, well, that's going to rationalize all those denominators by squaring them. So that right there just becomes 29, cancels out the square root. Okay, so I've got now a rational number right here. Okay, and then the 3 squared is 9, the negative 2 squared is 4, and the 4 squared is 16. Since they have a common denominator of 29, I can add up the numerators and I get 29 over 29, the square root of that. Well, the square root of that is just the square root of 1. And so therefore the magnitude of d cap is 1. And d cap is a unit vector. Okay, we've got some information here to go over in terms of unit vectors and unit vector notation. And then the homework is listed right here. Recall, for vectors in 2 space, the direction is the angle the vector makes with the positive x-axis, which is counterclockwise. So those are vectors in 2 space. Okay? All right, thanks for watching. I know it was a bit of a long video for this one, but it's the introduction to algebraic vectors.